Okay, so we're going to keep talking about nucleation, and this time we're going to talk a little bit about growth, and both of those things and how those things influence the size distribution. Okay, so last time we introduced this idea that there's a barrier to nucleation, and the barrier results from the surface tension. We've got two different quantities here to worry about. There's the energy of precipitation, which goes up as the particle size gets bigger, because we're trying to get stuff out of supersaturated solution here. The more you get out, the better. So the energy for precipitation goes up as the size of the particle gets larger, but you also make more surface area. And the surface area to volume ratio becomes really unfavorable at small sizes. One goes as r cubed, one goes as r squared. You get a barrier because of that. And this leads to something called a critical radius. A critical radius is a concept that relates to the supersaturation of the system. Because remember, the supersaturation changes this equation in a way. It changes the driving force for precipitation. So it moves this part of the equation around. And when things are really supersaturated, then this R star gets smaller. Right? We looked at a couple of different R stars for different values of supersaturation. So when the solute concentration is really high, little particles become stable to dissolution, because the driving force for keeping that, for making that tiny little thing goes up. And that radius, right? Not only the supersaturation, it's also dependent upon the surface tension. So the surface energy of the crystal you're making is a really important quantity for defining this barrier. If they're really, if the tension is very large, then this thing becomes large. And the barrier height responds accordingly. Okay, so the barrier height is a strong function of the supersaturation and a strong function of the surface tension, both quantities to worry about. Now, let me just say one thing about this. This barrier here is not like a traditional barrier that you're used to thinking about in a chemical reaction. It's actually a thermodynamic barrier as opposed to a kinetic one. So the system's got to traverse all these different sizes, and it has to get over this size that's very unstable. But that's not like a transition structure. It's not like a transition state. It's a ground state energy of one of the particles on the trajectory. That's very different, okay? And as a chemist, I didn't think about that when I first saw this. Now I'm very deeply skeptical of that, because most chemical reactions have some sort of kinetic barrier that they have to overcome. Okay, so kinetic barriers might be actually on top of this. This might be the minimum barrier, and any additional activation energy to push it over this size might be something to consider also. It might be that this thermodynamic barrier is relatively small, and the only thing that matters are kinetic barriers. I see some scowls in the audience. Do you have an opinion about what I just said about kinetic versus thermodynamic barriers, or a question? Yeah, so sometimes in a reaction, you might have a pre-equilibrium between two starting materials. Let's say it's like a typical situation is a transition metal catalyst where a ligand's got to fall off. Okay, and you have to make an undercoordinated metal complex. And then the undercoordinated metal complex goes and does some reaction that has a barrier associated with it. Okay, when you write out the expression for the kinetics, the equilibrium constant between the dissociated form and the associated form is very important. Okay, so the barrier to doing the reaction might be largely controlled by the barrier to forming the dissociated complex. That's sort of a thermodynamic description of the reaction, the difficulty of performing the reaction. There's also the transition structures that have to go from these ground state things that are relatively stable. You would have to overcome some bond breaking reaction that adds a few extra kcals per mole over this equilibrium that could be the primary driving force. That would be a way to think about it. It's sort of analogous. Ethan?
Wait, so just to clarify, is what you're saying that like each size along the path of growth is basically a lot longer lived than a transition state would be?
Yes. Yeah. Yeah, because there are also going to be kinetic barriers to growing or dissolving a size. So you could make this R star and put it in solution and it would live for a while because there has to be some kinetic process to attaching to it or dissolving it. So each one of these is actually, each point along this line is a minimum. All right, so this thermodynamic picture is how engineers and applied mathematicians like to think about this problem. And it gives rise to this really wacky nucleation expression we talked about, where the nucleation has this extreme dependence on the supersaturation, and it gives you this crazy step function where the kinetics of the reaction turns on explosively fast when you hit the critical concentration, right? And you can see that by looking at what the nucleation time for, I think this is water droplets and water vapor, or it might be ice and water, I've forgotten which, you know, it's incredibly sensitive to the supersaturation ratio, right? This is a factor of 2 in concentration. Amazing. All right, so that's the thinking on that. Last thing, we talked about each of these different types of reactions. We have this precursor conversion chemistry. We're going to revisit some of that today. We got the nucleation step, we've got the growth step. Each one of those things is linked by the solute intermediate. There's also this thing called Ostwald ripening that we talked about that tends to kick in when the reactions reach steady state and the solute concentration is low. Then this sort of dissolving to make solute and precipitating again leads to exchange of monomers between particles. That leads to a ripening, meaning a increase in the size, the average size, and a decrease in the number, right? This guy's going away. Number of particles drops, particle size increases. All right, so the main goal of the discussion today and of my research for a long amount of time now is to really understand the kinetics and the mechanisms of each of those steps and how they contribute to controlling the size and size distribution. I've forgotten whether I've shown you this view graph once before or not, but these are a bunch of electron microscope images of different colloidal crystals. And actually, these are co-crystals of 2 different colloidal crystals. This one is palladium and iron oxide. It's really easy to recognize iron oxide because they make these perfect spheres. Perfect spheres, kind of like these guys up here. Those are probably iron oxide also. And because they're so perfect and so monodispersed, where they're all the same size, they do this close packing thing. They naturally form these super lattices or supercrystals of nanoparticles. This paper done by Elena Shevchenko, she was here recently and gave a colloquium talk. She was a postdoc with Stephen O'Brien here at Columbia when she did this work. And I love this picture primarily because it really speaks to the diversity of materials that arrive in this state. So you've got oxides in here, there are halides, there are metals, there are metal chalcogenides of several different varieties. And they all make perfectly monodispersed samples. Bizarre. It's really unusual. Why would they do that? Okay, so we'll talk about the explanations today. So as I said, the typical one was proposed by Lemaire, or at least he's attributed as having provided the guess there. Lemaire said, well, it's because of classical nucleation theory. And in one of these reactions, what happens is that you supersaturate some medium, you push the solute concentration, which I've written as monomer concentration here, above the equilibrium solubility limit. You push it into supersaturated territory, you keep going, and then all of a sudden, watch out, critical concentration, and wham, nucleation takes off as a step function, right? Super sensitive to concentration, rapidly producing many nuclei, and then those nuclei all work together to consume the solutes that are present. And that pushes the concentration back down, and that shuts it off. And because nucleation is a step function of concentration, it turns on and off in this narrow region of time here. All the crystals grow, and then they reach the equilibrium solubility limit where they begin to ripen. Okay, so it's this short burst of nucleation that gives you a narrow size distribution. Number one answer, if you were to go to a conference on colloidal crystals and poll the audience and ask them, this is what most of them would say. So the other explanation stems from mechanisms of growth. Okay, so we have to talk about growth kinetics to follow that. And there's sort of two regimes that people consider. One is growth by diffusion, and the other is growth by attachment. So by what I mean growth by, I mean limited by. So we're interested in the rate determining step of the growth process to define its sort of mechanism and what the kinetics are. In some situations, diffusion becomes slow. When growing large crystals, this is often true. So to follow this, you have to consider what happens near the particle. So here's your particle in gray. It has a radius that's defined by this R. And then there's this thing around it called the diffusion sphere. Okay, the diffusion sphere is a region that gets depleted by consumption of monomers. So the crystal is chewing up the monomers faster than they can get replaced. And the concentration of monomers around the crystal drops. This creates a depletion of monomers nearby, a drop in concentration. And the region around that crystal where the monomers are and that concentration is dropped is called the diffusion sphere. It is labeled with a dimension delta here. Okay, so let's take a look at the solute concentration. Sorry, this y-axis is not labeled. This is the bulk solute concentration. And really, this is the solubility is what I should be saying, not the solute concentration. This is the solubility of the bulk material. Okay, it's right there. This is the solubility of a nanoparticle with radius r. And here is the, let me think about this for a second. Am I saying this wrong? I've labeled as concentration of monomer. Yeah, and it drops as you get toward the crystal. So this is the concentration of monomer in bulk solution. That's right, this is not solubility. But this is solubility. That doesn't seem right. No, that's right, because this is supersaturated. Okay, sorry about that. So this solution is supersaturated relative to the solubility of the crystal. That's what I wanted to say. So remember that Gibbs-Thompson expression relates the solubility to the bulk solubility modified by this radius and surface tension term. Okay, so a small thing becomes more soluble than the bulk material does. During a crystallization, you have some solubility, you have some monomer concentration that's supersaturated. You're above the solubility of the particle. You're above the bulk solution by even more. And if you look at that monomer concentration as a function of position, here's delta. This is this diffusion sphere delta here marked. What you'll find is that outside of the diffusion sphere, the concentration of monomers in the solution is what you would expect. And then as you get closer, that concentration drops until you reach the surface of the particle, and then it hits some value, arbitrary value, CI. Okay, so if CI is greater than CR, you have more monomers in solution than the nanoparticle wants at equilibrium, right? This is the solubility of the nanoparticle. So if we have more monomers than CR, there's a driving force for precipitation to occur, which there better be. Okay, so you get this depletion width. Let's take a look at the fixed law of diffusion here. So the growth rate under one of these processes can be described by the flux of monomers to the surface per unit time. Okay, number of monomers that reach the nanoparticle surface per unit time, and then you can define this as passing through a sphere of radius x. Okay, so you know the diffusive sphere could be that radius x, for example. And then the growth rate is really just the surface area of a sphere times the diffusivity of monomers times the concentration gradient at each position of x. Okay, so around the particle, you know, the closer you get, the gradient goes up, the x gets smaller, yada yada yada. This is just a standard diffusion expression. And it comes out as moles per liter per unit area per second. All right, so if you want to take this thing and make a linear growth rate out of it, you actually have to add volumetric units. So this is just a unit conversion. So now what we're doing is we're normalizing this growth rate to the surface area of a sphere. And if we multiply by volume of each of the units, so we're not doing moles anymore, now we're doing how much material in terms of cubic centimeters or something like that. You can calculate how fast the radius of the particle changes. It's just unit conversion. Here is geometry. Here is concentration and number of moles. All right, so if you take this expression and integrate from R to R plus delta, now from here to here, you end up with what's called the diffusion controlled growth rate. Okay, and this is, again, we've got the diffusivity here, we've got R, we've got delta, and then this quantity in parentheses. This quantity in parentheses is the difference between the monomer concentration at the surface and out in bulk solution. So this is the amount of stuff that has sort of been consumed here. Okay, so the growth rate is related to the difference between those two. It's this amount of concentration times these terms here, and diffusivity being one of those. All right, so think about this for a second, because I feel like I might have put this in too soon. Oh, wait a minute. Sorry. Okay, yeah, I got this in here too quickly. I'm going to go like this. I think that'll do it right. There we go. Did I get that in the right spot? Almost. Okay. All right, let's try this again. I need to do this one here. Go like this. There we are. Thank you. Okay. Now I have to reorient myself. All right, so let's consider the other case, okay? I'll back up quickly. This growth expression here is called the diffusion controlled growth expression. And it's expressed as moles per liter per centimeter squared per second. Let's talk about another situation where instead of diffusion to the crystal being limiting, attachment at the crystal surface is limiting. Okay, so here's a case where the growth rate is really just going to be, so the growth rate in this situation, we can forget about this diffusion sphere stuff. Let's just take a look at this difference between CI and CR here. So this is, again, the solubility of the crystal in the solution. If the concentration of monomers at the crystal surface is higher than the solubility, you will get precipitation. And so the rate of forward growth of that surface is just the amount of solute in solution that's above the solubility limit. That's the concentration that is available for precipitation. We actually have the same volumetric growth rate here, dr dt, but in this case, the kinetics of growth are related to some surface attachment rate constant and then this concentration we just defined, the difference between the surface concentration and the solubility. Okay, so this is basically a simple, like, first order rate expression. You've got a rate constant, you've got a concentration. And here we've actually added units to account for the fact that this thing is a sphere to get the flat surface growth rate. Okay, so this is surface area of the material times some value of K, moles per centimeter squared per second. And then this is the amount of excess solute. A little bit simpler rate expression. It's linearly dependent upon the excess solute concentration. All right, so let's take a look at limiting cases. Let me just say, first of all, that it doesn't have to be one way or the other. Okay, it doesn't have to just be surface attachment limited or just be diffusion limited. You can actually have contributions of both things. And what that's going to do is it's going to push this concentration around, as you'll see. All right, so let's consider the case where diffusion is actually equal to the rate of surface attachment. Okay, so at steady state, those two quantities kind of have to match each other. So if you take the diffusion equation here and you take the surface attachment equation here and you set them equal to each other and then you rearrange, you end up with this interesting expression that looks at the ratio of CI minus CR and C bulk minus CI. That's just the ratio of these two dimensions on this graph here. Okay, that ratio actually sort of tells you which mechanism is operative, and you can reduce this piece down here to get this thing like this. Okay, so this ratio is dependent upon the attachment constant, diffusivity, and the dimensions of that sphere. All right, so let's consider two situations. One is where the diffusivity is very, very small, okay? And it actually much smaller than the product of this attachment rate constant and the radius. Under those conditions where diffusivity is really, really small, well, you're gonna, basically diffusion is gonna be the thing that dominates the growth kinetics, and it's gonna push this CI down towards the solubility of the particle, okay? So that quantity CI minus CR goes to 0, and let's see here. Did I substitute in for this one? I forgot exactly what I did. I guess it boils down to the diffusion limited growth rate. That's right. So, and then if you express this thing as a linear growth rate, you get an equation that looks like this. Okay, so this is basically the diffusion limited growth expression written out in terms of radius, for the change in radius with time. So when that diffusivity is dominant, the monomer concentration approaches the bulk solubility, and the only thing that's determining the rate of attachment is how fast those monomers can get toward the surface and try and push that concentration up. Now, the reason we did all this is to show you that the rate of growth is actually dependent upon the radius here, okay? So different particles in an ensemble will have different rates of growth. This is the key finding. The radius dependence of this thing makes diffusion limited growth very interesting, as we'll come back to in just a second. Let's do the other case first. This is one where the diffusivity is much faster than the attachment reaction. Okay? If the monomers have no trouble getting to the surface, but when they reach the surface, there's a surface attachment limitation, then you're not going to get a diffusion sphere anymore. In fact, they go to the surface and they get rejected. So there's no depletion that happens. The monomer concentration is just going to be the bulk concentration. And if you take the surface here, this is really, you could replace this just by C bulk if you wanted, minus CR, like we've done down in this position here. So you take this volumetric growth rate, you stick in your value for G, and you solve for this thing. And now it's just, the radius is just the surface attachment rate constant. You got to add the volumetric units here. This is just the volume of a mole of material. And then this concentration difference. All right. So when you have surface limited kinetics and no diffusion sphere, now the radius does not enter into this other than the solubility. The radius does not enter into this equation. So there is no radius dependence of the linear growth rate. Okay. Now, this has a really big consequence because it was pointed out a long time ago that diffusivity, that diffusion limited rate constant, and I should have actually used this expression here on this next plot, this 1 over R dependence gives rise to something called size distribution focusing. So, if you have an ensemble of crystals and the crystals are growing under diffusion limited kinetics, the rate of growth of the smaller ones is larger than the rate of growth of the larger crystals. So these guys will grow faster than these guys do. And with time, the distribution of the ensemble will actually compress and become more narrow. Okay? That's called size distribution focusing. And it's a consequence of the volumetric growth rate under diffusion limited conditions, not the one written here, but this one here. All right, so this is well known. People were very interested in this because actually Tadao Sugimoto, whose papers are assigned for you to read, and he goes through all these derivations for you, discusses them, and you should read through his paper. He was very interested in having narrow particle size distributions because he was primarily interested in making silver halide colloids for photographic films. For a long time, before there were computers, people took pictures using photographic films and light sensitive colloids, and those colloids are made from silver chloride and silver bromide. And so the particle size distribution and the size of the particle was very important to the resolution of the image and the processing of the films and whatnot. So they were focused on trying to understand why it was possible and how to do a better job of controlling the size distribution. And Sugimoto noted this aspect of the diffusion limited growth rate, which was actually first pointed out by Howard Rice, who's a student of Victor Lemaire's, probably a graduate student here at Columbia, actually. And Sugimoto came up with this description that relates this size dependence of the growth rate to the supersaturation. Okay, and so I'm not going to really walk you through this too much. but you can read about it in his paper. All right, this is the growth rate. So we got change in radius with time on this axis, and this axis is this quantity R. So this is actually a solute concentration, believe it or not, because these units here are RC. So this is actually critical radius. This is so this is different values of the critical radius. And basically, when the solution is very highly supersaturated, the critical radius of this thing shrinks, right? So if you have to think about this in terms of pick a particular size, let's say 5 nanometers or something like that, and you change the supersaturation such that the critical radius becomes 1 nanometer, you're way out here on this graph. If the crystals are even larger, they're way out there. If the size is down here in this region, you actually end up in a situation where some of those crystals may actually want to dissolve. They become less likely to grow. But to get into a focusing regime, you actually need to be above about twice that critical radius to get that ensemble far enough away where all of those crystals want to grow in size rather than dissolve. So down here, you might imagine that we're going to do Ostwald ripening, right? Ostwald ripening happens under conditions where the crystals are in equilibrium with the solute concentration, or they're at steady state, I guess, with a given solute concentration, and some of them will dissolve and some of them will grow. You have to get to about twice the concentration of the solubility of that particle before the distribution really begins to focus well. All right, so the point of that graph is just to say that the higher the supersaturation, the more significant these focusing effects are. Okay, and this has been a very important principle in people's minds. If you want to make a narrow size distribution, one of the things you do is you push the monomer concentration up as much as you possibly can. That gives you the largest impacts of this diffusion limited growth situation and the greatest narrowing of the distribution. All right, and there's a very famous paper along these lines by Xiaogong Peng, the magician, and his PhD advisor, Paul Alivasatos. And actually, for those of you working in my group, this is Juanita Curtin. Her name used to be Wickham. So this paper's been cited over 2,000 times, not very common for a synthetic chemistry paper. And it's all about standard deviation here. This is the particle size distribution in 2 different experiments for cadmium selenide and indium arsenide. And what they note in this paper is that the distribution drops. Okay, it's narrowing as the particles are growing, and that narrowing is particle size distribution narrowing, okay, or size focusing. And then they did another experiment where they injected a bunch of material in at a later time, made it grow fast again. And by supersaturating the solution, they could actually shrink the distribution again. Okay, and so this single experiment was used as evidence that particle size distribution focusing occurs. Unfortunately, these are really small numbers, these changes that they're observing here. And they made a couple of very significant assumptions in this paper. All of these measurements were actually done by looking at the width of this peak. Okay, here's an absorption spectrum for a quantum dot. The width of that transition tells you about the polydispersity. If you have multiple different sizes, you have a broader peak. Okay, so what they're actually analyzing here is peak breadth, and they're calling it standard deviation. Guessing the standard deviation. The problem with this is that you have to assume that a certain width of an intrinsic size. So let's say you had a perfectly monodispersed sample. How broad is this peak in that case? What they said was that it was a line. Okay, and they use that assumption in fitting the changes to that peak. And it turns out it's not a line. And in fact, in this particular spectrum, this is the width of a single size. This sample is perfectly monodispersed, or very nearly so. Okay, so if you look at changes to this width, it's not telling you about the particle size distribution at all. It's telling you about the intrinsic breadth of a single particle. So that was one of the major things. They had to assume that the size distribution curve of a single size is a delta function. It also makes the assumption that that the distribution arises from a burst of nucleation. I'm not going to spend time explaining that to you, but let me just say that the interest in this particular observation is evidence that this is the other mechanism that people have in mind when describing narrow polydispersities, but it's not based on sound analysis, especially this assumption about the width of the absorption spectrum. I'm going to just, for the sake of fun, because we're not going to go into this in any more detail, I've actually plotted the widths of the absorption spectra of lead sulfide quantum dots on this graph versus the energy of their transition. Okay, so this is a given particle here, 1300 nanometers or so, just under 1 electron volt. So somewhere right here. And you'll see that the width of particles of that size is about 75 MeV or something like that. If you make a larger particle, the peaks get narrower. And if you make a smaller particle with a higher energy transition, the peak gets broader in energy. Now, on this same graph, we've plotted in black here and also this green star measurements of the width of a single size. Okay. So what you can see is that if you just had a single nanoparticle and you looked at its absorption spectrum, it actually broadens as you get smaller. And the total width is not much greater than that. Okay. So in all of these samples here, all these red and yellow samples, the width of the ensemble, all of the full distribution, is almost equal to the width of a single size. So none of these distributions are very broad. They don't, the polydispersity doesn't impact the width very much at all. And actually, just growing the particle from here to here makes that peak get narrower, and has led many people who didn't think about this to conclude that the polydispersity is narrowing because the peak is getting narrower, right? Peak gets narrower, that tells you the polydispersity is narrowing. That's wrong because of the size dependence of the intrinsic breadth. So this is to say that the size distribution focusing stuff and using the absorption spectrum to draw that conclusion is flawed. And so neither of these explanations is really sufficient to explain why nanoparticles have a narrow size and size distribution. Yeah.
Have people tried like reanalyzing the data from the previous experiment by like taking this into account?
No. It's a nice thought. Yeah, and in fact, for cadselenide, this is not known as clearly yet. There are, the other problem is that things like shape can impact breadth. Surface chemistry can impact breadth. So it's hard to do the analysis of their study without knowing exactly the sample they were working with. But that's a nice idea. Okay. Yes. All right. So I am not satisfied with state-of-the-art understanding of why particle size distributions are narrow in any system. Quantum dots are the best case scenario for studying these kinds of problems for a whole host of reasons. And even under those conditions, it's not known why the particle size distributions are narrow, or it's not widely known. So we'll come back to that depending on how far we get today. But we're going to take a step away from that for a second and talk about some of my group's work on precursor conversion chemistry and how that's an important quantity. So we've talked about this before. The solute supply kinetics are really important. And there are sort of different regimes. You can have a case where the breakdown of the precursors to make solutes is slow compared to the consumption of solutes by growth. Or you can have another scenario where it's fast and everything sort of piles up here. So if it's slow, it turns out that you can use that reactivity to control the outcome of the crystallization. And that's a really good situation to be in. So let's talk for a minute about what's happening. You know, I said to you during the nucleation phase, you make nanoparticles, and those nanoparticles consume the solute, and that pushes the concentration down. Okay, so this nucleation turns off and turns on and turns off thing is actually governed in part by the consumption rate of the solutes by growth. So let's think about this. There's sort of two different reactions that can take place. You make your solutes. The solutes can go and make a, whoops, I got the title wrong here. This should just say nucleation. Solutes can go and make nuclei, and perhaps it has some rate expression like that. For the time being, we'll assume it does. Remember, this is the classical nucleation rate. Or solutes can add to nuclei, or they can add to any other nanocrystal in the solution. And let's just sort of take a attachment limited growth expression here to help think about that. All right, so during the course of this reaction, solutes are made, nuclei are formed, nuclei and nanocrystals consume solutes. And what ends up happening is these two manifolds, the growth manifold and the nucleation manifold, are kind of in a competition with one another for the available solutes. Eventually, the number of these crystals becomes so high and the size of them becomes large enough that this consumption by growth way outstrips the rate of that reaction. And this process will take over and that process will shut off. In general, this is true for any kind of a reaction where you have initiation followed by propagation. If the initiation phase is has a higher concentration dependence than the propagation phase, you'll get this sort of competitive scenario where the slow thing shuts off the higher concentration thing. And that tends to lead to narrow polydispersity in polymerization, for example. If you have a polymerization where the chain initiation is a second order function of the monomer concentration and growth is a first order function, you get narrow polymer weight distributions because growth drives that concentration down and this thing shuts off quickly. All right, so there's this competition that's going on here, and Sugimoto said, all right, well, we like classical nucleation theory. This makes a lot of sense to us. It's very useful. We got the step function where this is so high, so sensitive to solute concentration that it's a really good on-off sort of a process. He said, let's take a look at a scenario where we change the supply rate. Okay, and he uses the term, the symbol Q to define that. He's got something that he calls his nucleation mass balance, where the rate of supply, which is the making of those monomers, is defined by this rate here, Q naught, in volumetric units. And those solutes either go to nucleus formation or nucleus growth, okay, according to those two arrows. What it doesn't go to is supersaturation, it turns out, which is confusing, and I'll come back to. But you have these two terms, growth or formation. Here's our growth expression here. And then here is our nucleus formation. This is the volume of a nucleus. So this is all in volumetric units. And the nucleus formation is a change in the number with time, okay? The growth equation is the number of crystals at any given time times the growth constant per crystal. All right, so you can account for all of the solutes using that very simple equation. Okay, so what Sugimoto did is he developed a silver chloride growth scheme that was very controllable. And one of the really nice things about studying silver chloride is that you can monitor the silver ion concentration and the chloride ion concentration using electrodes. Okay, so he could put an electrode that was selective for those ions into his crystallization reactor and monitor their concentration in real time. And he had all kinds of schemes for changing the supersaturation. One of them was that he would just take a syringe that had silver in it or chloride in it and squirt it into the solution, very concentrated solutions. He could squirt them in with control. So that was one way for delivering monomers to the solution. Another one he really liked was that they used a mixture of gelatin and silver ion, and gelatin helped make the films, I think, at the end of the day. It helped to passivate the particles and make a colloidal dispersion. But the gelatin could be hydrolyzed in the presence of acid, and it would actually release silver ion into the solution. So he would break down the gelatin, release silver into the solution, and this led to silver chloride formation. And in this experiment here, what he's doing is actually adding different amounts of acid that breaks down the gelatin. But he could have done this with a syringe as well. And so he's run 5 different crystallizations here, and he's plotted the supersaturation ratio. So he knows the solubility of silver in this medium. He knows the solubility of chloride in this medium. So he can determine the supersaturation ratio in real time. Very, very powerful stuff when monitoring these reactions. So here's one where a lot of acid was added, and it makes the crystallization go quickly. Silver is released rapidly. The solution supersaturates fast. Here's one where only a little bit of acid was released. Silver is released much more slowly. It supersaturates more slowly. And notice how all 5 of these curves kind of peak at the same value of S. So why are they peaking, first of all? Why is it going back down again? What's he monitoring? He's monitoring silver ion concentration and chloride ion concentration. So why are they going down all of a sudden? You're growing a crystal of silver chloride. So the crystals are consuming the solutes. This is a Lemaire-like curve, supersaturating, nucleating, and then growing. Okay. So all 5 of these reactions seem to nucleate at the same value of the supersaturation. That's pretty cool. That sounds an awful lot like critical concentration dependence, right? That's what Sugimoto thought also. You know, you hit this critical concentration, boom, nucleation takes off. Nuclei are formed, and then the nuclei consume the silver and chloride in solution, and the solute concentration drops and the supersaturation goes down.
We also seem to be approaching the same value.
Oh, the final value.
Is that attached?
Well, so what is S equals 1?
Oh, is that one?
Bulk solubility is equal to the solubility in solution. Yeah, so this is equilibrium. Above 1 is supersaturated, below 1 is undersaturated. That is a good point. Just like in our Lemaire picture, these guys are approaching the bulk solubility. Okay, so the thing that's changing, however, is the rate at which solutes are being generated by this breakdown of gelatin at the nucleation. So here it's fast and here it's slow. And what he said was, all right, let's measure the slope here at each of those points. We're going to call that Q naught. That's the rate of solute generation during nucleation. And then he compared that rate to the number of crystals. This is your N again. The number of crystals at the end of the reaction increases as you go to faster and faster rates. Okay, so now we're looking at solute generation kinetics going up. The final number of crystals you get out is sensitive to that. Okay, you can use this cartoon that we made on the previous slide here to explain that. The rate at which you make these things defines how many crystals you produce. Why is that? Sorry, I should have gone this way. Okay. The simplest explanation for this is for the nucleation process to turn off, the concentration of solutes has got to go down. Right? What makes the concentration of solutes go down? Growth. Growth makes the solute concentration go down. As the number of crystals in the solution increases, the magnitude of this pathway goes up, and eventually this pathway becomes faster than the solute supply. Okay, so growth takes over, and it consumes all the solutes being generated, and it allows this concentration to go down, and then this turns off, right? Because this is an on-off function. This is a step function, according to Sugimoto, and that graph certainly makes it look that way, right? It looks like a step function because you hit that concentration and boom, all of a sudden it starts heading down. Okay, so the number of crystals goes up and up and up until that number is sufficient to drive the concentration down, and then the number stops going up, right? Is that shut? And then concentration going down shuts off nucleation. So you can take this expression here and solve it by making the assumption that the solute concentration during the nucleation phase is constant. You assume that the solute concentration during nucleation is constant, then this equation here boils down to this very simple relationship. The number of crystals that you produce is equal to the solute generation rate divided by the growth rate. Okay, those are those two arrows on the left, and one producing solute and consuming it by growth. That ratio determines the number. Really simple. Fast kinetics, you get more particles. Fast supply kinetics. The other side of the coin is that if the crystals grow really well, if they grow quickly, this is an important thing to remember. If the crystals grow quickly, you will not produce very many, because the crystals that are present are sufficient to consume the solutes. They're so good at growing, they suck up solutes with a very small number of crystallites being present. Okay. That is a somewhat counterintuitive result for people, I think, that the number would be related to the growth kinetics. And that growth kinetics being faster would reduce that number is not very intuitive. Right. The part of that doesn't really appear in this much at all is the nucleation rate. You know, we just said, let's just call it a step function. It doesn't even matter what its true form is. As long as it's pretty strong dependence on concentration, you're going to get this sort of a relationship where the number is really dominated by these two terms. Nucleation is kind of an unimportant reaction in these processes, it turns out. All right, so let's take a look at what you can do with that. So one of the things that you can do is to design compounds that control crystallization kinetics by adjusting the rate of the solute supply. Okay, so we talked about how important that is. If you have compounds with different structures and different reactivity, you can just pick a molecule to define the breakdown kinetics very simply. And so my group has worked on these thio and selenoureas, where E is sulfur or selenium, and you end up with a huge range of reactivity depending upon which structure you make. And because these compounds are really easily synthesized, it's it's straightforward to make thousands of them They're cheap and abundant and whatnot. And there's a huge difference in reactivity of these molecules. This guy is about 1 billion times slower than this one. Huge difference, 1 billion. Now, it depends, the reactivity of these compounds depends upon the metal cation that you mix them with, depends upon the surfactant medium you put them in. It also depends upon the temperature, okay? And all of those things are variables for us. We want to grow all kinds of different materials. And so, you know, what we want is to be able to pick a molecule that adjusts this solute supply kinetics independent of all that stuff. We want to be able to just go dial it in and not worry about the solute generation rate. Change the temperature, change the surfactants. You still have control over that step. That's really powerful, particularly for size control. All right, so here's an example reaction that we've been studying to death. It's the combination of bisphenol disubstituted one here with lead oleate. We have a slight excess of lead because the stoichiometry of the lead sulfide you make has excess lead oleate bonded to the surface. That's actually size dependent. So if you want to make a really small crystal, you actually need more lead oleate because the surface area to volume ratio is higher. So you can set the amounts of these guys just as you like, let them react, and then we monitor the formation of lead sulfide using a dip probe. You can stick an optical fiber into your solution and measure the amount of absorbance that way and determine the yield of material. So here are 5 reactions where we're changing this para-substituent out here on the phenyl group, and it changes the kinetics. Electron deficient compounds like this fluorinated one are much faster to produce lead sulfide. Electron rich ones are much slower to produce lead sulfide. So that variation in kinetics is really quite powerful. Here's a Hammett plot showing, I don't know, we're not going to talk about the Hammett sigma parameter, but it's an empirical relationship that tells you how electron deficient or how electron rich these substituents are. And there's an expectation that the kinetics of the reaction will be sensitive to this electron deficiency or electron richness in a sort of systematic way. And our reactions they do behave that way. And that just says that these reactions are very well defined. But if you take those different molecules now and you look at the nanocrystals at the end of the day, what you'll find is that the rate of the reaction, so this is a rate constant that was taken by fitting this to a single exponential. You take that rate constant out here, you'll find that a slow reaction produces fewer nanocrystals than a fast reaction. This is the same thing that Sugimoto did, right? He plotted Q naught, which is a rate, for plotting a rate constant and showing that there's a correlation between that rate constant and the number of crystals that form. Of course, the number is related to the diameter, the size, because each of these reactions is done on 10 millimole scale. So we're making 10 millimoles of lead sulfide, and if you change the number of crystallites that you make, you change how big the crystallites are. Okay. Yeah.
This might be a silly question, but would you be able to optimize like the solute, or sorry, the solute concentration? Like, if you're able to optimize that, what would determine the maximum size of crystal you could make? Because it seems like that rate is like very dominant. So like,
Yes.
what would be the actual max? Like, what determines the actual maximum size?
Good question. So it turns out that it's controlled by temperature. And so that has the biggest impact on the size. This rate stuff is within a certain temperature. And it really only works when the supply rate and the growth rate are comparable. So like, let's say the supply rate's really fast, then it doesn't matter how fast, if you make it faster or slower. You know, the solutes are all made at once, and then the kinetics of their crystallization is what matters. If it's really, really slow, you run into a problem where the crystals tend to stop. They don't want to grow anymore unless the solution is hotter. Okay, well, I'll show you this in just a second, but you know, so in nanoparticle science, and in all the examples that I'm aware of anyway, the final size is dictated by the reaction temperature. All right, so so one of the nice things that you can do here is, let me see how much battery I have left. Perfect timing, huh? Okay. So one of the things you can do with all this stuff is use it to control size very nicely. As I've said, it's a powerful way to control size. And you know, normally when people grow a batch of nanoparticles, they just stop the reaction early. They kill it before it's finished to get the size that they want. That's bad news because it leaves behind a bunch of starting material. I can't unplug that thing. How annoying is that? Do we need a wireless router in here? All right, well, I'll try and record myself this way. I don't think anybody was plugged in anyhow. So, yeah, it just makes the isolation of the final product and its purification a lot better. There's the thing. But why am I not seeing my screen anymore? Oh, darn it. Okay, well, the router needs to be plugged in for the projector to operate. Oh boy. Well, I think that's the end of our lecture for today. So next time we'll finish this discussion. Does anybody want to ask a question about this stuff? Probably there is some relationship. But also the supersaturation. And then, you know, the final size. You know, one of the reasons why distribution focuses on unity is that it really only works on very small length scales. And you have to work some relatively large length scale. So I don't know how that always is, you know. starting on some of the properties. And, you know, it turns out, as we'll see next time, that distribution bubbles are very important. So the actual calculation can't really be done until you know the mechanism. Okay, sorry for the debacle here again. I will see you on Monday.
Thank you.
You're welcome.